So, uh, uh, yes, okay. So, yes. So the aim of lecture is introduce DG algebras and DG categories, and so probably I start with a slogan. So hopefully you will agree with me after this talk. So the slogan is that somehow for me, the DG algebra somehow makes derived equivalence. I think most of our interested in somehow easier. That's my slogan. So we'll see. So let's start with definitions and examples. So let's, for simplicity, we walk over a field. So just recall that by a graded algebra, we mean really Z graded algebra. So 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 it has a decomposition as a vector space. So P runs through Z. So by graded algebra, we mean 2 points. So first, that A power P times A Qs is contained in the A P plus Q. And the identity element belongs to the zero component. So remark. First of all, for elements in AP, so we write the degree of A is P. So with such element is called homogeneous of degree P. So actually we only consider, so somehow we only consider, so this is one trick that in the TG case, we only consider homogeneous element in the TG setting or the graded setting. So this is degree homogeneous element. Later we only consider homogeneous morphism or graded morphisms. And so we just take A, be a graded algebra, then by a graded derivation of degree, say degree M on A, by graded derivation on of degree M means, first of all, it's a map from A to A. So 2 points. First, that this map has degree M, meaning that i.e., so it sends piece component to the P plus M, so for any P. So this map is degree M. Secondly, the derivations have satisfied the graded Leibniz rule. So this partial A times B, I mean, both A, B are homogeneous, as we said. This partial A times B plus, there's a sign. So the degree of A times degree of partial is M in this case. A for any A and B in M. By default, they are homogeneous. So an interesting fact is that if partial A from A to A is a graded derivation with the degree of partial odd, this is odd, then partial square. So this odd is a condition, is a necessary condition, meaning that the composition of partial and self. So this is also a graded derivation. Is a gradation. So this is somehow important because later we want to hope that partial square is 0. So being if partial is odd degree, for example, it's plus 1 degree, then this to prove that the partial 0 is partial square is 0, we only verifies on the generators of the algebra A. Okay, so this is so then we comes the first definition. So a so-called a differential graded. We always degree algebra. We always abbreviate this as a DG. So a DG algebra is a pair. Where A comma D with A graded algebra, a Z graded algebra, and D is from A to A is a graded derivation. Of degree plus 1, and such that D squares 0. So this is a formal definition of a DG algebra. So just a remark for this definition. First of all, this D is called the differential of A. So somehow the DG algebra is a graded algebra together with a differential. Secondly, so since D squared 0, then we can talk about cohomology. In this case, the cohomology becomes an algebra. So first of all, it's clearly graded. So because for each P, we have the cohomology group, say cohomology space, and it becomes an algebra. I mean, how is the multiplication? So indeed, so assume that A is in HP of A and B, and both are cocycle. Then the multiplication of these two classes, just the multiplication. I mean, so here we have to show that AB is a cocycle of A. This is because of Leibniz rule, the graded derivation. So in summary, that the cohomology of the DG algebra becomes a graded algebra. So let's talk about example. I will spend some time on examples. This is hopefully examples are more important than theory somehow. So the first and trivial example is that a graded algebra A is always DG algebra, meaning that if take the zero to be the differential. So in particular, ordinary algebra, which is our main concern, I think. The ordinary algebra, say phenomena, just change another notation, is always, I mean, ordinary algebra is viewed as a graded algebra, concentrated on degree 0. So it becomes a DG algebra. So it's always viewed as a DG algebra concentrated in degree 0. So because it's concentrated in degree, so the differential has to be 0. So this is also so we always view ordinary algebra as a DG algebra. So this is some kind of trivial example. Second one is also somehow trivial. Assume that you already have a DG algebra A. You have several ways to cook up new ones. First of all, you can define the so-called opposite DG algebra. opposite. We use this all op. First of all, as the graded space is the same, but the opposite multiplication, so we use dot upper op. So this is a new operation. It's nothing but you sort the positions, but you have to add a sign, the causal sign. So we have add sign a. Sorry, so the differential is the same as a graded, but the multiplication is with a causal sign. So this is one way to have a new algebra, the opposite of GG algebra. So you have to take care of the minus sign. Another thing is that we have another algebra, the so-called sometimes we can call it the truncated. This is the truncated DG subalgebra. So it's a subalgebra, DG subalgebra, and obtained by truncation. So we usually denote by this. So the truncated from degree 0, and we throw away positive degrees. But this is a good truncation, so be careful. I mean, so the negative degree stay the same, but the first degree is not A1, A0, but the cocycles of A, and others are 0. So it's really a subspace, a great subspace of A, and it inherits all the stuff. It inherits the multiplication, the subalgebra, and also the differential. So this guy is a TG subalgebra. And yes, so somehow we have this picture, many of us. So this guy is truncated sub, so it's included. So this inclusion is included. But we have a projection, canonical map from this to this. But be careful, this guy is concentrated in degree 0. So this GG algebra concentrated in degree 0. So these two arrows are both homomorphism between DG algebras, meaning that the homomorphism of graded algebras and commutes with the differentials. And yes, one is inclusion, another is a projection, because the cohomology group is a quotient of. So let's say both are DG algebra homomorphism. I mean, I think it's clear how to define DG algebra homomorphism. So this above two examples somehow trivial, but let's start a non-trivial one. So this one will play a role in tilting theory, classic tilting theory of complexes. So we will see. So for tilting theory, usually let phenomena be a K-algebra, be an ordinary K-algebra, K-algebra. We start with a complex X, so it is complex. So this is a complex, a cotangent complex. Complex of right lambda modules. That's yes. So for a complex, then we can talk about a DG algebra, the important one, the DG endomorphism algebra. So this is actually I think the most important example in theory for us. The DG endomorphism algebra. So you already know by this end of lambda X of X. So how to define this guy? The DG endomorphism or algebra of a complex. So as a graded space, for each component, for each P, each component P consisting of graded maps from F to X, graded maps F of degree P. So meaning that the F sends the nth degree to m plus p degree. So in other words, you can write this as an infinite product. So this home is a module category, xn, x. But usually we like view this F as a graded map, not the infinite product. Not so you will see that it's better to view the elements in the piece degree as degree graded endomorphism of degree P. This is more convenient. So the first definition is permanent. And the differential that's denoted by partial. The differential of the DG algebra HP. So given a degree P map from X to X, we have to get a plus one map, endo map somehow. So we just time. Oh, sorry, we should X. We compose with and minus P degree F compose dx. To be careful, I mean, this is because F is degree P and the differential is degree 1. So this new and this morphism is degree P plus 1. This is what we want. And you can prove that it's really oh, sorry. So it's clear that how to compose. I mean, the multiplication of this guy just compose of graded maps on X. So just a Euro composition. So then this guy is a DG algebra. It's called so-called DG endomorphism algebra. And more interestingly, that the cohomology algebra of this one is sometimes is what we need. So this is as a graded algebra is this big coproduct such that the home in the homotopy category of Euro module category. So this is important one. And there's X and shifted of X. So this is isomorphism. You can even write equality, I think. Yes. As graded algebras. So somehow you see that if you are only care about triangulated categories or say homotopy categories, you only have this cohomology algebra. But somehow later you will see that it's more convenient to consider the DG endomorphism algebra, not just the homology algebra. It's not enough. So this is one example. For each complex over an ordinary algebra, you definitely have a DG endomorphism algebra. And usually this DG endomorphism algebra has non-zero component both in negative and positive degrees. So the fourth example is that so this is you can compare with Bernhard Keller's talk. So I just say I think Bernhard might repeat some of this. By a graded quiver, we mean a quiver together with a function. So this guy is a function, h. Sorry, this is a function. So so this Q is a quiver. Really, we want that the number of vertex is finite, but the arrow may be infinite. But and a degree function, a graded function. This is a map from Q1, the arrows to integers. that means for each arrow you give integer, maybe positive or negative. So given a graded quiver, then the path algebra is graded. Remember, this grading is not the length grading. For example, if P, so if P is for example alpha 1, alpha 2, alpha L is a path, then the degree of this element in the path algebra is summation of alpha I from 1 to n. So in this way, this path algebra is graded. So a so-called by TG path algebra KQ comma D, we mean a graded path algebra KQ as above. I mean, so associate to a graded quiver. First of all, we have a graded quiver, then we have a graded path algebra as above, and its D is a differential, meaning that it's a differential of degree 1. And usually we want that to satisfy such that D on each idempotent is 0. So remember, for each vertex you have a idempotent. So then this guy is sent to 0 by the differential. And whenever you have this D, the differential, then you get a DG path algebra. Why is related to next talk by Bernhard? It's the following fact. So any map, just remember any map D from D to Q1 to KQ, meaning such that for each arrow you send an element D, but to be careful, this D should D alpha should lies in this subspace E T alpha KQ E S alpha. So here for S alpha, I think most of them know. So for arrow, we write this S alpha is starting point, T arrow is the ending point. So any map, such map, given you just assign for each arrow to a D alpha. This is a combination, linear combination of some paths, but from starting from S alpha and T alpha, extends uniquely to a graded. Sorry, you have to be careful. You have to, yeah. So here we because we still asking that this degree of this guy is +1 for each other. So this so given such a map such that D alpha, the degree of D alpha is alpha +1, then this D extends uniquely to a graded derivation of degree +1. But yes, remember that we want this for each idempotent is 0. So this is always we want. However, the extended, the obtained, the graded derivation, this D, second D, usually is not square zero. So somehow this is very non-trivial. The non-trivial, I just say the non-trivial condition, D square zero, actually it corresponds to a infinity coalgebra structure. Not one-to-one, but locally, so-called locally finite. I will not expand this. Locally finite A infinity coalgebra structure. I think locally on the shift of this space K. Remember that the space of arrows is graded. Then we have to shift this. So anyway, so this is so that's some kind of one-to-one correspondence between DG path algebra and the A infinity coalgebra. So in this sense, that these two conditions are more or less equivalent.
Is this the same as some kind of a bar construction?
Yes, right. Yes.
Okay.
I probably Bernhard later will talk about the co-bar construction, but this is a dual one. So far, is there any more questions? So I more or less I finished the DG the examples of DG algebras. So yes. Should I continue? Yes. Okay, so probably I continue. So that's the DG algebras stuff. Actually, we like to have DG modules.
There is a question in chat.
Yes.
Can you
please?
So D has to reverse to send an arrow to a path of the opposite direction.
Yes, I write the composition from right to left. So for example, this alpha equals, I hope that this is agree with S alpha, this is idempotent, then alpha and this idempotent of T alpha. This is my notation. I mean, I go from right to left. Then I think it should be fine, right?
Yes.
So for example, this alpha should start with E S alpha, then T alpha. So Z is the idempotent. So E I square is EI. I hope this is fine. Okay, I continue. Yes. So next, we should talk about DG modules and the derived degrees. Very good. So for now, this subsection, we just fix a DG algebra. A and D. Usually, I'll also write the DA. So what's DG module? So this right, I just write right. You can also talk later left. Right DGA modules. So it's also a pair. So first of all, M is a graded. Oh, sorry, it's a right graded module. Right graded A module. So this is starting point. So this means that first of all has a decomposition as before, and this is the right action satisfy that A to the q's power x on MP lies in MP plus q. So this is graded module, and with a differential. Oh, with a differential. It's dm from m to m. So first of all, this dm should be degree plus 1. And this dm square is 0. So this is m is a cotangent complex. And you have to compatible with the module action. So you have to this Leibniz rule. So this m a plus there's a sign. That sign is given by this m. So remember, we always assume this m is homogeneous. Yes. For any m m a. So this is the Leibniz rule. Okay, so this is the I think this should be clear. I mean, this is you can put it simply like right DG module is nothing but a module somehow enhanced in some category of cotangent complex. But let's just remark. Actually, personally, I like left modules. So so you can define a left A module, a left TGA module. So it's n plus a differential. So the n should be a left graded A module together with a differential. And the Leibniz rule goes like this. The Leibniz rule a n, so for any a in a, n in the module n homogeneous always. So the Leibniz rule is like this: d a n plus minus a degree. Remember, a d. So somehow you switch the differential, the position of differential and a differential degree 1. So this is Leibniz rule for the graded A module, and you have that just notice that a left DGA module n is nothing but a right DGA op module. So we usually like this. For example, given a left A module, how to write the corresponding right A op module. So for example, if A is a left, n is a left A module, and the corresponding right action, just using this is right action. It's nothing but there's a sign, the causal sign and an. So this is the corresponding between left and right. Always have sign. And then you can also define. You can define a DG AB by module. I will not repeat this, but this means that you have another DG algebra B, then you can have a DG by module. So this is this is quite not so difficult. So actually, we want to start all the right DGA module. So, for example, A itself is a right module. So by my case, so we denote by CA the abelian category. The abelian category of all right A modules. The abelian category of A modules. So all the right modules. So how is homomorphism? So here homomorphism. So I tell you another. So homomorphism F from so assume that M is a DG module, N is another right DG module. A homomorphism you have to satisfy 4 things. First of all, this M have to be degree 0. This map. So this map, that is this map with degree 0, preserving the morphism. And F should be a graded morphism between graded modulus. And finally, F should be compatible with the differential. So this is the morphism. And maybe most non-trivial is that such a morphism F is called a quasi-isomorphism. Quasi-isomorphism. If it's a quasi-isomorphism between the underlying co-chain complex. So if the cohomology induced map between the cohomologies, isomorphism. So this category is, as I said, this CA, sorry. So this CA category is an abelian category. So, and for example, the kernels or co-kernels is the same as in the category of co-chain complex. And then we as usual, we have a co-chain complex. So then we have to talk about the homotopy category. So this is a little bit different from the Euro one. So we have to define what do you mean? Let's be a morphism. So for example, in CA, so this two DG modules and a morphism. This morphism is called non-homotopy. So if there's a homotopy, but here the homotopy should be careful. If there's a map from this guy of degree -1, so careful, here we have to be careful what you mean. So meaning that this will send MP to MP -1, but actually should preserve the module structure. This is somehow a little non-trivial. So for all the A, so this actually should preserve the module structure such that F is equal to Dn composed with H plus H composed. So having this, then we have now we have the homotopy category Ka, the homotopy category. The homotopy category of EGA modules. So we know that objects of this category is the same as objects in CA, is the same. But the morphism are same in the homotopy category if and only if their difference is non-homotopy. Now, and the composition are induced by the Euro composition. So this is the homotopy category of DGA modules. And a proposition, so this, maybe I give a proof. So the Ka, the homotopy category has a canonic triangulated category structure. Triangle category. To be a triangulated category, so you have to do two things. One, you have to talk about the shifts, the translations. The translation is easy on this category. So having a module, we have a shift of this module. So for this, I write out for each module how to define this. First of all, this shift is created like this. So somehow this is like a cosine complex, and the differential is minus sign. The same action, write a module action, write a action. So then you can prove that this is the shifted one is also a right DGA modules, and then this is the translation on the homotopy category. This is well defined. And the exact triangle is more complicated. So for this, that's a standard proof in Keller's paper. So a short Euler sequence for this, a short Euler sequence in CA like this. So actually this means that are morphisms, but the underlying graded modules to this short sequence. Right? So this is a short sequence with with morphisms F and G are both morphisms between DG modules. So this short sequence is called graded split. If it splits in the category of right graded A modules. So as a graded modules, this sequence splits. So such short sequence is called graded split. So then, so you can find in Benha's 1904 paper says that this CA is a Frobenius category. Frobenius category, exact category. With conflations given by a great split short Euler sequences. And I mean, having a Frobenius category, we always consider a stable category. Is stable category something coincide with the homotopy category just defined. So then by a general result of, say, in Harper's book, then you see that this is triangulated because it's a stable category of Frobenius category. So the derived category of right DGA modules usually denoted by DA. So this is nothing but this is homotopy category. Then we localize all the quasi isomorphisms. But you can also view it as a Worldial quotient of this guy modulo all the acyclic. Acyclic means that as a DG module is as a complex is acyclic. So such from a triangle subcategory when we quotient out, then this is a derived category. So the derived category also have a triangle structure. Just maybe after this remark we have a break. So let lamina be algebra, ordinary algebra. We always view lamina as a DG algebra. Then DG lamina modules is nothing but a complex, a co-chain complex of or modules, nominal modules, right modules. We only talk. So then we have such we have this abelian category is nothing but the abelian category of cosine complex of module category of, and the above defined homotopy category is nothing but the unbounded homotopy category of cosine complex. And the D-nomina. So we always view nomina as a DG algebra concentrated in degree 0. Then this is nothing but the module category, the unbounded dual category. Good. So yes. So you can say that the derived category of DG algebras is an extension of the unbounded derived category of ordinary algebra. Yes. Could we make break maybe?
Yes, I think now is a good time. But before, if there are some questions, maybe.
Yes, yes. If any question, just tell me. Yes, any question.
Maybe I don't know what's a Frobenius category. Can you quickly explain a bit?
You mean the triangulated category, right?
Mm-hmm.
Yes, yes. Sorry. So triangulate. So I
No.
think you know the filling category. Filling category that meaning that you have you can take kernels, co-kernels. In particular, you can talk about short exact sequence in any abelian category. So but related category then you don't have short sequences. But so maybe I just say one word.
No, sorry. I mean Frobenius categories, not triangulated categories.
Oh, Frobenius category. Oh, okay. Sorry. Frobenius category, yes. Frobenius category, yes. So here I use Frobenius category. Yes, you're right. So meaning that, thank you. This. So abelian category, or more generally, exact category is Frobenius. If it looks like a module category of a self-injective ring, if first of all has enough projective objects, this means that for any object, you have a projective objects and a deflation, a surjective map somehow to this guy. This P should be projective. And you also have enough injective objects. So meaning that for any object Y, you have a Y includes in some injective objects. Most importantly, that last one is projective objects equals to injective objects. So meaning that an object is projective in this category if only if it is injective. So, and the typical example is that the category, if given a self-injective ring, then you take, say, a quasi-Frobenius ring, then you take the module category of this ring, then it automatically becomes a Frobenius category. So because injective modules are same as injective modules, projective modules are same as injective modules. But then the general notion applied to exact categories looks like this. And for that proof, this CA is Frobenius. Then you should talk about the injective objects in CA and projective objects in CA. Actually, both are so-called contractible modules. They are more strong than acyclic modules. Something like the mapping cone of the identity map. So then you should prove that it has enough. So any objects is embedded into such objects, and any objects there's a surjective map from such contractible module to this guy. So then one proof that it's a Frobenius exact category. Yes. Yes, and a non-trivial result, a very non-trivial result is that the stable category of forbidden category is naturally triangulated. So then in this case, one proves that the homotopy category is triangulated. Yes, I hope this answers the question.
Yes, thank you.
Thank you, thank you. Let's just 3 more minutes. Right.
Okay. So maybe we can start at 12:45.
Yeah, just 1 minute, 1 minute.
Okay. I mean, we can have about 6-7 minutes break if you like.
Okay, yes. Can we restart?
Maybe we can start. I thought that maybe you want to
Yes,
start
can we restart?
in. Do you want to start right now? Is it okay for you?
Okay, maybe I just start. So we just defined for any DG algebra, we talk about the homotopy category. Later we talk about the derived category. Certainly our main concern are the derived category. And there's a non-trivial result, a theorem. So assume this A is a DG algebra. We have a canonic recommend. So first of all, in the middle, we have the homotopy category of DG. And here we have the acyclic modules. This is a triangulated subcategory. We have to the video quotient, then we get a derived category. So this is inclusion. And this is a canonic. CAN means canonic. So this is somehow subjective. But so this non-trivial part is here, they have a joint. So this P is the left joint of N, and I is a function. It's a right joint. So well, it's X tends to PX is the so-called DG projective resolution of a DG module X. So somehow in this case, for the in the classical homological algebra, we have DG project resolution, but here you have to talk about a DG project resolution. So I will not define it, but you can be it's given by some adjoint functor of the canonical functor from homotopy category to derived category, and this I for each DG module X, you have IX. The IX is called DG injective resolution of X. I mean, having this resolutions, then you can have derived functors and so on. There's another theorem. The derived category, this guy, is compactly generated. Meaning that first of all, has infinite coproduct. I mean, so this infinite coproduct is just given by coproducts of DG modules. Most importantly, it has generated by a set of compact objects, small objects, compact object. I will not define compact, but and the compact objects of this category is the smallest six subcategory generated by A itself. So and this category has a particular notation called by per of A, the so-called this definition. The per perfect derived category of DG algebra, of the DG algebra. I just prove, or just not prove, I mean just schedule proof. So actually, one can prove that in the homotopy category, in the derived category, usually the home in the derived category is very hard to compute. But if the first entry is nominalized is A itself, then this is quite easy. It's nothing but the there is the homology of M for any DG module. So from this isomorphism, you can show that A is a compact object and even a compact generator for the derived category. And then we show the category of compact objects is the CCAR of A by general result on compact generation triangulated categories. So this isomorphism is canonical. So far, this is DG modules. I just very quick, but the idea is clear that having DG algebra, you have to study DG modules, but the DG modules should be compared with cochain complex of usual modules, and then parallel to the classical treatment. Then we have the homotopy categories and derived categories. We have resolutions for complexes and then for this case we have resolutions for DG modules and so on. And this derived category is nice, although it's very big. It's compact generated, and the compact object is controlled by the regular module A itself. Then we have the perfect derived category of A. So maybe this, at least for this lecture, I don't know how far I can go, but for the application part, this is maybe we are most concerned with application of DG algebras. I mean, why we are concerned with DG algebras? Why we need this? So I in my mind, I have several results to support this. First of all, you find in Ben-Hakkara's famous article said that have this kind of, somehow we see that we just see that the derived category of A is a certain compact generated triangular categories. Somehow the next theorem I would say that is the converse of this theorem in certain sense. So how to say that? Let T be a algebraic. I will explain this. Algebraic triangulated category, which is compactly generated by a compact object, by a single compact with E, let's say E. Then Bell said that T is is equivalent to the derived category of for some DG algebra. So somehow that if this category is generated by a single compact object E, then this is nothing but our derived category. And here they have assumption this algebraic. What's the meaning of algebra? Let's prove this. I mean, in the proof, I will say that let's prove this. So algebraic assumption means that by definition, a triangulated algebra means that this T is the stable category. The state is isomorphic or equivalent to the stable category of some Frobenius category, some Frobenius exact category. Frobenius category. So this is so meaning that, but why did such categories called algebraic? I think the philosophy behind that most I can say most triangulated categories appearing in algebra are arising as a stable category of some Frobenius category. The reason. So then, I mean, assume that T is the algebraic triangular category. Then we have this. This is we identify this, but actually there's equivalence between the stable categories by the so-called acyclic complex of P. So well, this P is the subcategory of the E, the stable, the Frobenius category, formed by all the projective injective objects. And this is the acyclic complex of homotopy category of P. This is the equivalence, actually. So I will not talk about in detail, but this object E in T correspond to some acyclic complex of projective modules. So this is P is the acyclic complex of projective objects. Then having P, then because P is a complex, so we can talk about the DG endomorphism. Remember that for any complex, you can talk about the DG endomorphism. Yeah. So having this, so then we can do why we have the function. So we identify this as this. Then we have this. And for each x is a complex of projective modes. Then we consider the home complex. So the home complex. The home complex. The home complex. So this is a home complex. And this guy is naturally induced by composition. It's naturally a right DTA module. So this guy belongs to the derived category. So you can prove that this category, this functor is a triangle equivalence. Yes. So this is so if you forget about the details, you can say that most nice triangulated categories in our fields are derived categories of a certain DG algebras. But everything has a price. You have to pay. The point is that usually the DG algebra is very hard to control. That's the point. But yes. Let's see. Another thing is that maybe a theorem. I don't know. Maybe it's this theorem is more good. A little trivial. Let's say let f from A to B be a homomorphism between DG algebras. Then Then you have forgettable functor, right? This for each module B, then this you can view it automatically as a module of A. Denote this functor by U. Then the point that U is equivalence if only if this F is a quasi-isomorphism. It's quasi-isomorphism as a complexes. So actually, how to prove this? So this is a little bit trivial because this U has a left joint. The left joint is the derived tensor, the induction functor actually. And this guy, this derived tensor sends A to B. And you see that then it's not too hard to say that so it sends the homology. I mean, this is viewed as a direct sum of P from derived category of A to sigma A sent to this guy to HB. Boom. So you see that if U is equivalence, then this adjoint is also equivalence. But this adjoint sends A to B and sends the homology of A to HB. So if U is equivalence, then you see that then you see that this is isomorphism. More or less, yeah, at least you can prove this one direction, I think. So in other words, that quasi-isomorphic TG algebras induce the same derived equivalence, derived categories. So this is we will use this fact in the next theorem. So I want to mention the following theorem. So this is the most remarkable since in our field, I think, in 1989. So this is the derived Morita theorem of Ricard. Later, Bernhardt developed the unbounded version. So let lambda and gamma be two K-algebras. Then we remember that the unbounded derived category is equivalent to the gamma unbounded derived category. If only if there exists a tilting complex P. I will not recall the definition of tilting complex, such that this A is isomorphic to the endomorphism in the derived category. So tilting complex is a complex of a bounded complex of finite generated projective modules over gamma, satisfy its self-orthogonal and generating the whole Dirac category. So the DG algebra, you see that there's no DG algebra in the statement, but the proof. So one direction is somehow easy. This is quite easy because what's the D? Assume that it's F, then the P is nothing but F nominal. Then because nominal in the right hand side has some orthogonal property, so one proof that the P as an image also has some self-orthogonal property. So this is somehow trivial. Sorry, this is not A. This direction is very non-trivial. So for this direction, we really need DG algebras. So this is why I said DG algebras makes the equivalence easier. So we take the DG anamorphism algebra of this guy. So this is really a DG algebras having negative and both negative and positive components. So remember that this A, you have the truncated, and they have the projection to this guy. And the homology of this guy is the zero homology is just the homotopy the home in the homotopy category of P, but because P is a bounded complex of projectives, so it's the same as the derived unbounded category of the anamorphism of this kind. So then this by definition is by assumption, this is isomorphic to num. And since P is self-orthogonal, then we know that this isomorphism, then these two are quasi-isomorphism. Quasi-isomorphism. I mean, both the inclusion and the canonical map. So roughly speaking, you can say that this DG algebra A is quite isomorphic to the nominal. And remember, we have a theorem. We have a theorem above. Remember here. We have a theorem here that DG, if quasi isomorphism between two DG algebras, then the derived categories are equivalent. So having this chain of quasi-isomorphisms between DG algebras, then you can even write down somehow the equivalence. So this is isomorphic to the derived category of A. So this actually also can be proved by the anyway. Just this is also the home complex. So this home complex becomes naturally a right DGA modules by composition of maps. So this is equivalence, but this A DG algebra. Then this you have this because it's truncated subalgebra is a DG algebra. Okay. This is forget functor. You can also have another forget functor. D nominal viewed as DG algebra, but this is nothing but the unbounded Dirac category. This is the same thing. And both are forgetful. This is forgetful function. It's also forgetful function. Forgetful. For restriction functors. So we're very explicit. Very explicit. So we have one applications in the tilting theory. So this is the original, actually this is really the original treatment of Bernhard on the derived equivalence between unbounded dual categories using DG algebras. This is actually using the DG anamorphic algebra. The final application I want to talk about is a result also well known to experts. So let's see. In the remaining, we assume that this phenomena is a algebra given by a quiver. So this is a finite dimensional quiver algebra. And yeah, so this guy is nothing but the composition. This is the radical of this composition. And there's an interesting things that associated to this algebra. So we defined the radical quiver of phenomena. So for this finite dimensional algebra phenomena, we associate a so-called radical quiver. Q tutor. So the vertex set is same thing as the Q0, but the arrows. So the arrow set, so the arrow set, we take the dual home. So this is the K0. So remember this radical phenomena has a bimodal structure over K0. We take the home dual. So this is as a bimodule over K0. And you remember that this radical phenomena has a multiplication. So radical phenomena views as an algebra without unit. So we dualize, because we have a dualizing on the algebras, and so we have a map. This map as some kind of co-algebra. The co-algebra, by dualizing the multiplication on radical radical phenomena. So since radical phenomena has an algebra structure, by dualizing, we obtain a co-algebra structure. Then this guy extends uniquely to a DG as a DG path algebra. So here, as a graded equivalent for any alpha in Q tutor 1, we want the degrees plus 1. Then you see that this D has degree plus 1. So this is what we want. We hope D is a differential of degree 1. And in this case, just maybe remark, the D square 0 correspond to the co, maybe, yes. I will, maybe I'll change another application. Such that D restrict to the arrow set is given by this delta. So this is better. So D square 0 correspond to the co-associativity of the co-multiplication. So as I said before, that the DG path algebra should correspond to some A infinity co-algebra, but in this case, it's really co-algebra, not in A infinity co-algebra. Anyway, we start from equivalent algebra, we get a DG path algebra. Well, this all arrows has degree 1. So this DG algebra is positive degree gradient. So we consider the homotopy category of the homotopy category of complex of injective modules over number. So by a result of Henning-Krauser, and it's more general, I mean, we are a very special case of this. So it shows that this category is compact generated. And more interestingly, that the compact objects of this category is a derived category of bounded. So somehow this is the compact generated completion of the bounded derived category of small module category. So the so-called Kurzweil-Moore duality. The Kurzweil-Moore duality says that there is a triangle equivalence. The homotopy category of injection modules is equivalent to the derived category of the above DG path algebra. So remember, we have a DG path algebra. For this, for simplicity, we just call this DG path algebra with the differential D. Remember, this D is induced by nominal. And taking both sides, we're only taking compact objects. Left-hand side is a derived category of modules over finite dimensional modules over number. Here side is the perfect category. So this is the so-called Kurzweil-Moore duality. So how to prove this? Indeed, this guy has an explicit compact generator. So it's given by the injective resolution of the semi-simple modules. Then we compute the DG endomorphism algebra of this complex. This should be isomorphic to the DG algebra. Yeah, roughly speaking. So this is the DG endomorphism. The injective resolution of lambda 0. By definition, is lambda over Vatican. So this theorem somehow put every finite dimensional algebra, quiver algebra, every finite dimensional quiver algebra into the framework of DG path algebra. So this is something I like very much. Yes, this is so. I think this is the material for DT algebras. So maybe I very quickly I talk about the DG categories and then just very quick, very briefly maybe. I see. This. Wait. I compare this. So although I have no time to justify this slogan for DG category, maybe I just write this. I mean, we say that following Kantrevich and Greenfield and others, we know that non-commutative scheme, I mean, this is never well defined, but one definition is that DG categories. So whenever you encounter suitable DG categories, you can view it as a non-commutative scheme. So in other words, the study of DG categories should be viewed as a part of non-commutative geometry. Why is that? The idea is that you replace any scheme X, you replace that by a so-called the DG category of perfect shifts of X. This is the DG category of perfect shifts, perfect coherent shifts of X. And why this replacement is effective? At least I have one thing to support this idea. So X is skin is smooth. Maybe we need this. We need algebra close or maybe roughly speaking. X is smooth if only if this DG category is smooth. This homological smooth maybe. This so-called homological. This is defined by Kantrevich. So in a certain sense, the DG category contains almost all the information about this classic scheme. Another thing, another idea is that you replace algebra, a DG algebra, maybe algebra seminar by the perfect. So here, this is I will define in a minute. You consider the finite generated projective modules, this guy, but now this is a bounded complex. This is the cosine complex, but you view it as a DG category. So you always replace algebra by DG category. Then, I mean, why this again? Why this is effective? So there's a result by Noven Vandenberg. Said that the Hodge cohomology of algebra A is isomorphic to the Hodge cohomology of this digit category. Moreover, this isomorphism leads to the co-chain level. The co-chain level has a big infinity structure and so on. So anyway, I mean, maybe you wonder, I mean, why this isomorphism is useful. At least say that if this TT category is the same or quasi-equivalence to another, then by the isomorphism, we know that this lambda and lambda prime has the same Hodge cohomology. But you may wonder what this means. You see, we see that immediately. We say that actually this happens if only if lambda and prime are derived equivalents. So maybe I will write another. Lambda and lambda prime are derived equivalents. This is derived equivalence, and only if the associated TG category are the same. I did not define the same, but more or less. So in this case, if this happens, then this the Hodge cohomology same. This is a modern proof. So I mean, this is a classic. I mean, the Hodge cohomology is a derived invariant. I mean, so that's now a modern proof that says any derived equivalence really leads to this DG algebra. These two DG categories are the same. So, I mean, because this isomorphism of Vandenberg, although this category is huge, but the Hodge cohomology of this huge category is the Hodge cohomology of this ordinary one. Yes. Sorry. So this idea of the why we like DG categories. Maybe very briefly. Sorry. Maybe very briefly because I have no time to say, but maybe at least I should give a definition. Then I put it. So the definition by a DG category. We mean it's a category enriched in the monoid category of complex co-chain complex. I mean, we can unpack this concise definition. I mean, this is just a category such as the home space is not a space, just is for any XY objects. The homes is a co-chain complex. And we want the identity object, identity morphism should be 0. And the composition. So this composition is a co-chain map, a chain map or co-chain map. for any. I mean, what it means by cochain map? Two facts. First of all, this is the composition morphism. The degree should be the plus of G. And the differential, I mean, both sides has a differential. The left hand side is the tensor complex of two complex, and this guy plus minus some. There's a degree of G. I mean, again, in setting we only consider homogeneous morphisms. Yes. So we have this Leibniz rule. Yes. So this is the definition of a DG category. And for DG category, for any DG category, this A, we always have the homotopy category. So this is just I mean, please don't confuse with the homotopy category of A modules. So this is completely different. For a DG category, the homotopy category usually denoted by this. So this category, the objects guy always the same as objects of A. But this category is the ordinary, say, pre-additive category. For two objects, this is the zero the homology of this complex. And the composition is induced by the composition in A. So this is the homology category. The idea is that for certain, we so-called I will not define this, for a pre-triangulated DG category, I will not define A. Its homotopy category H0A is canonically triangulated. It canonically becomes a triangulated category. This is then roughly speaking, this A is a DG enhancement, enhancement of the above homotopy, the triangulated category. So for any triangulated category, we talk about the DG enhancement, meaning that you find a pre-triangulated DG category such that its homotopy category coincides with the given triangulated category. So this is the definition of DG enhancement. So there's a technical assumption that's pre-triangulated. So this goes back to Bond Caprano. Bond Caprano. So maybe I just end with at least example. Actually, this example is the most important example, I think. So what's example of the DG category? So let lambda be a K-algebra, any K-algebra. Then we have the DG category of modules. So the objects of this DG category is the same of the objects in this abelian category of cochain complex of white module. But the home is different. The home complex, I call home complex. The home complex for any complex, only two complex, we want to find a new complex. How to define this? So this is very similar to the DG anamorphism algebra. For example, the piece component of this complex is nothing but f from x to y, but this map, the degree of this map, f is degree p. And the partial differential of this complex is similar print. That f is the dy composed of f minus p. No, this p. So then this becomes a home complex, and if then this kind of home complex we can compose just given by composition of graded maps. So then this compose defines a category and even a DG category. And the interesting thing is that this DG category is pre-triangulated. Actually, the homotopy category of this guy. I mean, this we don't change any objects, but the homes is the H0 of the home complex. But the H0 of the home complex is nothing but the homes in the classic homotopy category. So this DG categories is nothing but the classic homotopy category. Therefore, this DG category enhance the classic. In other words, that whenever you consider anything in the triangular category of the homotopy category of complex, you should come back to the DG category because this guy enhances. So this is, I think, yeah. And let's say. And I just maybe two remarks. One remarks that if we take all the small DG categories has actually several has model structures. So then this is quite important because, for example, it's tabuada. Wait. This is quite important because there you can talk about covariant resolutions, or in Drinfield's paper. In Drinfield's paper, he calls semi-free resolutions. So this is quite important. And you can talk about the DG modules over DG categories. For example, if phenomena is, remember with phenomena, we should replace this algebra by this DG category. Right? Actually, the derived category of this guy is equivalent to some kind of Morita equivalent. It's equivalent to the derived category of modules of this DG category. This is similar to, I mean, in spirit, it's similar to some kind of Morita theorem. Not surprising. So this is similar to the above isomorphism due to Lewin-Vandenberg. yes, it's. I think I just stop here. I mean, because I think certainly I have no time for this DG category stuff. And yes, I hope that the examples of DG algebras I gave will be helpful in tomorrow's talk by Bernhard Keller. So I stop here. Thank you very much.
Okay, thank you very much. Can you hear?
Yeah, thank you. So if you have any question, just tell me. So let's see. Is there any question? Not yet.
Yes. Can you hear me, Xiao-Wu?
No. Yes.
Xiao-Wu?
Yes. Xiaofa, I think now you can speak, I think.
Yes, I think the audience can ask questions now.
Yes, please.
Can you maybe explain why we need this model structure?
Yes, thank you. So model structure, actually, for example, let's come back to the DG. For me, I think maybe not correct. So for example, you have for the DG for triangular categories, we have several DG enhancements. Then you should compare, I mean, how they are unique, how up to what extent they are unique. I mean, to consider this uniqueness, then you don't study in the category of DG categories, but you have to model certain relation like quasi-equivalences. I mean, to make this theory work, you need some model structure in the sense of equivalent, so that you really consider DG enhancement in that homotopy category in the sense of equivalent. So in that sense, we need the model structure, I think. Also, in the model structure, it's clear why you need to do resolutions for algebras or for resolutions for categories, so-called cofibrant resolutions.
Yeah. So
and also in doing DG quotient, you need to do such cofibrant resolutions. In theory, you need to do this.
Yeah,
Yes.
But yeah, what confused me was just that in practice, if I only want to compute derived functors, for example, in practice, I do the same thing by taking projective resolutions and so on. So that's why I wonder.
That's some problem. If you always work over field, it's fine. But otherwise, for example, that's what let's so assume that A, for example, if A is a K algebra, but non-flat, then somehow when you talk about the tensor product of A and A, is somehow not so correct. So usually you should replace this by this. First of all, you take a quasi-isomorphism, a surjective quasi-isomorphism. For here, this A is a flat DG algebra. I mean, this here actually implicitly you are using model structure of DG algebra actually. Then you replace this guy by this is more correct things to do. Then you have some correct results. But if K is a field, then you don't need to do this. Yes, that's what I know.
Okay, thank you.
I hope this helpful.
Yes, but so you mean if I do this comparison using the model structures, then the upshot is that in some sense I get a unique DG enhancement?
No, that's far from no uniqueness. Whenever you establish some uniqueness in that homogeneous category, you get a famous result. But
okay.
actually, I think to define the uniqueness, that's the correct way. But to prove something is unique, that's very hard.
I see. Thank you.
Yes, but to state some theorem of uniqueness, then you should take care of the model structure, I think.
I see. Thank you.
Yeah, thank you.
I can't see somebody raising the hand, but
Yeah, yes. I hope I prepare enough material for Bernhard and Xiaofa.
Are there more questions? I think Xiao cannot hear me. Can?
Yes, if not, yes.
Okay,
Yeah,
thank
thank
you.
you very much for your attention.
Thank
And so I'm
you.
sorry for the technical problem of this
Okay.
Zoom.
Tomorrow we'll start with Bernhard. Okay, thank you very much.
Yes, thank you. I'll see you tomorrow.
Yeah, okay. Bye.
Thank you.